All right, we're back here on Tuesday, March 2nd. We're continuing chapter 23, calculating some electric fields for basic configurations. Where are we? We've calculated the electric field for a point charge before, and we saw electric field for a line charge. We saw that if you have a group of point charges, we can use superposition to get the electric field due to the several point charges. You can use the basic solution for a line charge, like a wire, to get the electric field produced by multiple wires. We're going to discuss solutions to the last two here, plane of charge and the sphere of charge today. Then we're going to get into parallel plate capacitors, and then do a few examples here. Homework 6 will be due Tuesday the 9th at 11:59 p.m. That's assuming I get this homework online tomorrow, Wednesday morning, before I have a full day of teaching. If not, I'll have to delay the homework for a day. Just sinking a bit right now. So here are the solutions to the four basic charge configurations that we're studying so far in the course. Solution for a point charge, solution for a line charge, and then these last two we're going to do today. So for a plane of charge, we're just going to state the solution. If you have a plane of charge here, and suppose that the plane's dimensions, the plane is much larger than the distance from the plane where we're evaluating the field, okay? In other words, the dimensions of the plane are much larger than the distance at which the field is being evaluated, so that the plane looks very large. In this case, the equation for the electric field is very simple, and it's just equal to the magnitude of the charge per area, the charge density, divided by 2 epsilon naught. And if it's a positively charged plane, the electric field in both directions, both sides points away from the plane, and if it's a negatively charged plane, the electric field vectors would be flipped, and they would be pointing toward the plane. Reason we're not deriving this, there's a much easier way to derive it using what's called Gauss's law, which we will get into in the next chapter. So for right now, we're just going to take the solution. So the main points here of this plane of charge solution is that the field strength is directly proportional to the charge per area, eta. So the more charge we pile on the plate per area, the stronger the field. Okay, that makes sense. Perhaps more interesting is that the field strength is the same everywhere. In other words, this is what's called a uniform electric field. By uniform, we mean that the magnitude and the direction of the electric field are the same everywhere near the plate. Okay, so that it produces a uniform field. And this becomes important when we discuss capacitors shortly. So what we're assuming here is that we're staying away from these edges here, staying toward the middle of the plate here, so we can neglect the fringing effects of the field. So what are some applications of this? Well, electrodes or any parallel plates such as capacitors, which use charged flat surfaces. So we'll get into this a little more later. The second solution that we're going over today is the electric field due to a charged sphere of radius big R. Okay. And this could be either a solid sphere or it could be a shell, okay? But the solution outside of a sphere is exactly the same. So suppose you have total charge plus Q distributed over the sphere. So that would be a charge density Q over volume as rho. The solution of that is Q over 4 pi epsilon naught r squared, or KQ over r squared. And this is the exact same solution that we would get if all the charge plus Q were at the center of a sphere. In other words, the electric field produced by a sphere with charge plus Q spread over its surface is exactly the same as if you put all of the charge at the center of a sphere, a point charge of magnitude Q. So the field lines just radiate, they're radially outward, so that's that unit vector r hat. That just means that the direction of the field at all points is radially out, and it goes as 1 over r squared. So this result is interesting in that you can put a point charge of charge Q in the middle, and it'll produce the same field as that same amount of charge distributed over the surface of a sphere. Again, we're not deriving. This problem is a mess to derive. The integral gets really messy. You have to use spherical coordinates, which most of you have not done much with. And we're going to go through a much easier way to derive this result using Gauss's law in the next chapter. So right now, just let's use this solution here. Take it for what it is right now. So now we have our 4 fundamental solutions, okay? Point charge, electric field, sphere of charge, and you see the solution's exactly the same, okay? Infinitely long line of charge like a wire, and infinitely wide plane of charge, okay? So these are our 4 building blocks, our 4 electric field solutions, and we can use these along with superposition to get the solution due to a combination of these. So let's go into parallel plate capacitors. Okay, so you might have heard, if you watch Back to the Future, the flux capacitor, or you might have seen the capacitors with circuits. So what is a capacitor? Okay, well, it's just 2 parallel plates, and each plate has an area A, and they're separated by some small gap D, and there's an equal and opposite amount of charge on each plate. So one plate has an amount plus Q, and the other plate has an amount minus Q. And the plates are separated by this insulating air gap, either air, or it could be a polymer if it's a capacitor, but some insulating material. So right now, let's just assume it's air. And there's a lot of applications of capacitors that we're going to be getting into in a few chapters. But one of the primary uses for capacitors is they're used to store charge. So in other words, they're used to store electrical energy, which can be later be given back to the circuit. One example is a defibrillator, okay, which is used to charge somebody's heart, hopefully get it back beating. And so this capacitor, if you notice, is neutral, right? You have a charge plus Q on one plate, a charge minus Q on another. So as a whole, the capacitor is neutral. The capacitors are charged, we'll see later, by connecting these 2 plates with wires and transferring electrons from one plate to another. So that's charging a capacitor. Don't worry too much about that right now. What we care about more in this chapter is getting an equation for the electric field of the capacitor, and then later on we're going to use this more in the upcoming chapters. So how do we get the field of a capacitor? Well, a capacitor is 2 parallel plates, so 2 planes. One is positively charged and one is negatively charged. And we already have the solution here for the electric field of a single plane, okay? It's equal to the charge per area, the magnitude over 2 epsilon naught. And if it's a positively charged plane, it points away from the plane. And if it's a negatively charged plane, it points toward the plane. So here's our solution again for a positively charged plate, right? You have a uniform field and it's pointing away from the plate. So here we have negative, we have two plates, which means we can apply superposition, right? We can add the solutions to the electric field produced by each plate. Okay, so let's see what that looks like. So let's start easy. Let's go outside the plate here. And so if we go outside the plate, we have the electric field E plus, which is due to the plus plate, and that's pointing away, right? That points away from the plus plate. And then you have the field due to the minus plate, and that's the negatively charged plate, and that's pointing toward the plate because it's negatively charged. So to get the total electric field, it's the sum of these two. But both of the fields are the same magnitude, right? Because the field is constant near a charged plane. So they both have the same magnitude, eta over 2 epsilon naught, but they point in opposite directions. So that means that the field outside the capacitor, the net field, is 0. The fields due to the plus and the minus plates cancel out here. Opposite signs equal magnitudes, vectors cancel. And you can go over to this right side of the minus plate, and for the same reason the fields cancel again, right? They're the same magnitude, but they're the opposite direction. And so the field outside of a parallel plate capacitor is 0. Okay, let's look inside between the plates here in this gap here. Well, in between the plate, the field due to the positive plate is pointing to the right, away from the positive plate. The field from the negatively charged plate is also pointing to the right because, remember, it points toward the plate for a negatively charged plane. And so in between the plates, you have two fields that are the same sign and the same magnitude. And so they're going to add instead of cancel. Okay, so the total electric field in between is E plus plus E minus is 2 times eta over 2 epsilon naught. And that's equal to the charge per area eta divided by epsilon naught. That's the constant, the permittivity of free space. You can also write charge per area. Oops, A should be in the denominator here. I've got a typo I have to fix. So it's the density, charge per area, and you get Q over A epsilon naught. It's right on the next slide, but I've got to fix that here. And so what that says is that in between the plates, you have a uniform electric field pointing from positive plate to negative plate, and its magnitude depends on the charge per area. So the more charge we put on these plates, the greater the electric field. So here's a summary of what we have, is that here's the field of an ideal capacitor, points from positive plate to negative plate. It's uniform, right? The direction and the magnitude's the same everywhere. So we say that there's a uniform electric field, and its magnitude is equal to charge per area divided by epsilon naught. Okay? Or we could call that eta if we want to put it in terms of the density. And the electric field is 0 outside. So this is something you should be able to do on a quiz or an exam. If you're given the electric field for a single plane, you should be able to use superposition to get the electric field in between the plates of the capacitor as well as outside. Okay, that's not too difficult. So this is an important result that we're going to use when we get into circuits in 2 chapters, when we're going to use a capacitor as a component that stores charge. So let's do a couple examples here. Okay, we're finished pretty much with the electric fields of the given configurations. Let's do a few examples. So suppose that we have a parallel plate capacitor, and it has two square plates. Okay, So the area is L by L. L is the length, and L is also the width since it's a square. And suppose that the plates are separated by some distance d, and what we want to know is what happens to the electric field strength under each of the following conditions, okay? So suppose first that we double the amount of charge on the plates. So in other words, we take plus q to plus 2q, we make minus q into minus 2q. We double the amount of positive and negative charge on the plates here. Okay, so we can predict that the electric field would get larger, right? So let's look at what happens here. So we go to our parallel plate capacitor formula, right? So like any problem, we find the formula which relates what we're trying to find, which is electric field strength, in terms of what we're given, which is the plate areas and the distance, okay? So here's the equation for the parallel plate capacitor. So we find the relevant equation. Now if we just double Q and leave everything else fixed, well, the electric field is going to double, right? Because if we keep the area constant, then the charge per area doubles if we double the charge. And so we're going to double the electric field. So doubling the charge on the plates increases the electric field by a factor of 2. Okay, so let's look at the next case. Okay, suppose we double the length. Okay, well, you might think, oh, well, the electric field's going to drop to 1/2. No, because this is one dimension, right? So if I double the length and it's a square, then I'm also doubling the width. So if L is doubled, I'm going to double the length and the width, which means that I am going to increase the area by a factor of 4. And if the area is 4 times larger and we don't add any more charge, then the charge per area is only 1/4 of what it was, and the electric field is also only 1/4 of what it previously was. So in other words, the electric field is reduced by a factor of 4. Okay, finally, what happens if we double the spacing between the plates? So in other words, we double D. Well, the electric field strength doesn't depend on D, right? So and if we double the separation between the plates, the electric field doesn't change because E does not depend on D. Okay, so here again, another ratio problem. You're going to be seeing these over and over and over, as you already have, on quizzes, exams, homeworks, because they're important. They describe the effect of the resultant variable, in this case the electric field, due to changes in the variables that influence it. So you should be able to do these problems on exams. Let's do another example here. So let's consider air. So you have a parallel plate capacitor, and it's square, and we have 2 electrodes that are 4 centimeter by 4 centimeters. Okay, so we know that, well, you can look up that when the electric field strength reaches 3 times 10 to the 6 newtons per coulomb, that's a strong enough field to break down air in causing a spark. In other words, we ionize the air molecules, and that causes a discharge which creates a spark, for example, a spark plug. So this is roughly the electric field strength needed to cause a spark in air. So given that, and given the area of the plates, what we want to find out is how many electrons must be transferred from one electrode to the other to create a large enough field to cause a spark between the electrodes. Okay, so this looks a little tricky at first because now we're talking about number of electrons. So let's just start with an equation which relates electric field of a parallel plate capacitor to its area. So here it is. Electric field is Q over epsilon naught A. Okay, and what we want to find is if the minimum field E is 3 times 10 to the 6 newtons per coulomb, how many electrons does need to be transferred? Okay, well, this formula doesn't tell us directly, but we can solve for Q, which is the charge that must be transferred. And if we know the charge and we know the amount of charge that each electron is, 1.6 times 10 to the negative 19 coulombs, we can calculate how many electrons must be transferred in order to produce the spark. So first let's solve this for Q. So we solve the parallel plate capacitor equation for the amount of charge that is needed. Okay, so epsilon naught's the constant. It's 8.85 times 10 to the negative 12 coulomb square per meter per newton per meter square. Okay, then we have to take 4 centimeters and convert it to meters. There's our area. And then we plug in the minimum field, and we find that when we plug in these numbers that the amount of charge that must be transferred is 42 nanocoulombs, where nano is 10 to the negative 9 coulombs. So 42 times 10 to the negative 9 coulombs. Okay? So if we know the total charge that must be transferred, and we know that each electron is 1.6 times 10 to the negative 19 coulombs, we can divide the charge by the charge per electron, and we get that we must transfer 2.7 times 10 to the 11 electrons, or 270 billion electrons must be transferred from one plate to the other to produce a strong enough field to cause a spark. And so this is another example here of a parallel plate capacitor formula. So let's do a final example here. So let's do an example with point charges. I don't think we've done enough examples of this so far, so let's do one now. So you have 3 point charges, Q1, Q2, and Q3, and they're at the corners of a rectangle. And what we want to do is we want to find what the electric field is at the 4th corner produced by these 3 charges. Okay, so we want to first find the total electric field in component form, meaning the x and y components. Okay, so we're going to use a coordinate system. As usual, we'll take y being up and x being to the right. So we want to find the electric field in component form, and then when we know the components, we can use Pythagorean theorem and the tangent formula to get the angle and the magnitude of the resulting field. Okay, so this is where, again, superposition, right? We know the field produced by a single point charge, and now here we have 3 point charges, so we need to calculate the electric field produced by each of these alone at this corner, and then we add up the 3 vectors. So superposition, it's just like when you added forces in physics 1. So let's do that. So we have to calculate the electric field due to each of the individual charges at this point P. So let's, and we add up all 3 vectors to get the total. So Q1, where's Q1? Q1 is right here. Q1 is a distance 2 centimeters from this corner, so R is 2 centimeters. Q1 has a magnitude of 5 nanocoulombs. Okay, so that's Q1. There's our distance. 2 centimeters is 0.02 meters. This constant, you can either use K or 1 over 4 pi epsilon naught. It's the same magnitude. And so when we add it all up, the magnitude of that field is 112,500 newtons. That points to the right because this positive probe charge here would be repelled by Q1. So Q1's force would be to the right, and so the electric field E1 points along the positive x direction, or we call that unit vector I hat. That's just a means it's in the positive x direction. So that's for bookkeeping. So now we found E1, it points in the plus x direction. Okay? You can plug in the same formula for Q2. Here's Q2. Q2 is positive, it's located 4 centimeters from this location. And the electric field due to Q2 would point downward or in the negative y direction because the positive probe charge would be repelled by the positive charge Q2. So we plug in a distance of 4 centimeters or 0.04 meters. We plug in 10 nanocoulombs for charge, and the electric field has a magnitude of 56,250 newtons per coulomb, and it points in the negative j direction, meaning downward in the negative y direction, which we denote by the unit vector j hat. Okay, so now we have our vectors E1 and E2. E3 is going to be a little bit more tricky, right, because it's at an angle. Okay, so the electric field will always be along the line coming from Q3 to this point. And in this case, it will be toward Q3 because the positive charge would be attracted, a positive probe charge place here, would be attracted to Q3. Right? This is negative, probe charge positive. Electric field would be along the line and pointing toward Q3. Okay? So the magnitude of Q3 is 5 nanocoulombs. The distance, we have to use Pythagorean's theorem, right? It's equal to 2 centimeters squared plus 4 centimeters squared to the 1/2 power. So that's the distance. Fortunately, it's squared in the denominator, so we just add the squares. And when you add these all up, this magnitude for this electric field E3 is 22,500 newtons per coulomb. And we can use trigonometry. This angle that it makes is 63.43 degrees from the x-axis. Okay. So we can write that in component form using the sines and the cosines, and we get this. So now we have all of the x components and we have all the y components, right? Because E1 only has a component in the plus x direction. E2 only has a component in the minus y direction. E3 has components along both, along the negative x and the plus y. So to get the total x component, remember we add up all the x components of the 3 vectors. To get the total y component, we add up all the y components of the individual vectors. And when you do that, here's our result. You get a field that's 1.0 times 10 to the 5 newtons per coulomb along x, and negative 3.6 times 10 to the 4 newtons per coulomb along y. So now we have our result in component form. Okay. Now once we know the components, we can use Pythagorean's theorem to get the magnitude of the net field, right? It's Ex squared plus Ey squared to the 1/2. So we square each of these, and we take the square root, and we get that the magnitude is 1.1 times 10 to the 5 newtons per coulomb. Okay. We can use the tangent formula, which is Ey over Ex, to get the angle, and we get that it's negative 19.4 degrees with respect to the x-axis, and that means it's clockwise with respect from the x-axis. Remember, negative angles mean we start in the x direction and we go clockwise, whereas positive angles means we start along the x-axis and we go counterclockwise. So I'm going to give you, you're going to get a homework problem on this, and this is definitely something that you should be able to do on an exam. You should be able to use superposition and the equation for the electric field of the point charge, and you should be able to add the vectors to get the total electric field, magnitude and direction, or the 2 components. I'm going to give you a homework problem on homework 6 related to this to get you some more practice. So that pretty much concludes today's lecture. Tomorrow we're going to go into the motion of electrons and protons in electric fields, the motion of charged particles in fields, and then a little bit about dipoles in electric fields. And then that will conclude chapter 23. So that's it for today. Go get some rest and have a good day. Thanks.